Today, I'm going to teach you some engineering topics. But first, let me introduce myself. I'm Professor Zar. In short, Professor. At the end of this video, you will learn how to balance redox reactions, basic solution, heat and enthalpy, solving for final temperature, nuclear reactions including alpha decay, gamma decay, positron emission, electron capture, and gamma decay. And lastly, carbon dating. Welcome to my show! Let's start solving on Zarmistry! Our first problem is about balancing a basic redox reaction wherein we have this problem. But first, let me give you a note. Hydrogen atom has positive charge and hydroxide has negative charge, while water or H2O has a neutral charge. So first, in this equation, chemical equation, we have to find the first half reaction. So I'm going to write now. And our second half reaction. Okay? And then after that, we have to find an element aside from oxygen and hydrogen and then balance it. So in this case, this element is already balanced. And also this is already balanced. So we move to the next step, which is to balance the oxygen. Oxygen first. So in this reactant side, oxygen is lacking one oxygen atom, so we have to put H2O on the reactant side. So this will turn to plus H2O. And as you can see, this is lacking some hydrogen atoms. So 3 plus 2 here is equal to 5. So we have to balance. We need 5 hydrogen plus there. And then after you balance, you move to your second half reaction. So as you can see, the product side is lacking oxygen here. So we have to add H2O again on the product side. 3 molecules of H2O because of 3 here. So as you can see, 3 times 2, so we have 6 hydrogen atom here on the product side. So we also have to add 6 hydrogen atom on the reactant side. After that, you check all the charges. This is your new equation. Check the charges. This has a neutral charge, and this has a positive 3 charge, so we have to balance it by adding 3 electrons. 3 electrons. And on this side, we have 5 charges here because 6 times positive is 6 minus 1, so we have 5. In here, we have negative 1. So for it to be a negative 1, we have to add 6 electrons on this side. So I'm going to delete this first. 6 electrons. So it is now balanced. The charges are now balanced, and all of the elements are now balanced. So we move to the next step. We should balance our electrons. So we have to multiply this whole equation by 2. So this will turn into this. Okay. So after the electrons are balanced, you can now cancel. You can cancel the electrons here, and then you can cancel 6 hydrogen here and there, cancel the H2O there, and then you will have a result of this equation. Don't forget the signs. Plus 2 CrO4, 2 negative. And then remember that you have H2O there, and then 4H plus here. So you will have a result of this equation. And actually, this is an acidic redox reaction. So after that, I'm going to show you how to make it basic. So we have here our acidic redox reaction. And it is acidic because of these hydrogen atoms. So for it to be basic, we should add hydroxide to the product side and also to the reactant side, because that's the law of conservation of mass. So we have 4 hydrogen atoms here, so we should also have a 4 hydroxide for it to neutralize. So 4 here also. So we're going to rewrite the equation because this will result into H2O, 4H2O. So our new equation will be this equation. 4 negative. So we have the same base here, so we can add. So 5H2O. So this is our basic redox reaction. The problem is all about heat and enthalpy. So we have this problem. How much energy is required to turn 20 grams of ethanol at negative 200 degrees Celsius into ethanol gas at 80 degrees Celsius? So before we solve that, we have to know these information. So the capacity or heat capacity of ethanol at solid, liquid, and gas form are the following: 0.97 joule. It's all in joule per gram degree Celsius, and 2.32 and 1.54 in gas form. So, and this 2 right here, which is the enthalpy change or phase change constants of ethanol, is 5020 joule per mole, and in vaporization it is 38,560 joule per mole. We have also to know the molar mass of ethanol, which is 46.07 grams per mole. And lastly, the melting and boiling point of ethanol, which is these 2. So this is a 5-step process. 5-step process. It is labeled, as you can see here, 1, 2, 3, 4, 5. So we have to plug in all of this information into this formula so we can get the energy total of this problem. So first, the Q is heat is equal to this formula, and then the enthalpy change is equal to this formula. So in this problem, we have to plug in the 20 grams. Specific heat of solid is 0.97, and then the temperature change is always final minus initial. So we want to accomplish this, so this will be the final, the melting point. minus the initial temperature of the ethanol, which is 200 degrees Celsius. So plus the enthalpy change, which involves the number of moles. That's why we have this molar mass. So 20 grams. Every 1 mole of ethanol is equal to 46.07 grams times this constant of enthalpy change, phase change, fusion, joule per mole. Number 2 and number 3, the energy required to liquid form of ethanol to gas form. We have to plug in our third step, which is 20, just the same, but here we are going to use 2.32 joule per grams per degree Celsius, and the temperature change, which is we are accomplishing the boiling point, which is equal to 78.37 minus from its initial, which is the melting point. There's no space, but this is 114.1 degrees Celsius plus the number 4 step, which is 20 grams, 1 mole again, over 46.07 grams, and times the constant of this heat of vaporization, or enthalpy change, phase change of vaporization, which is 38,560 joule per mole. And then lastly, we have to calculate the heat when it's in gas form. So 20. The specific heat of gas, we are using this. And then finally, the final temperature that we are going to use is, we want to achieve this, so 80 degrees Celsius, coming from 78.37 degrees Celsius. So after you add all that up, so you're going to get 29,566.3 joules. So we have this answer. So try it for yourself so you can check. That's it for heat and enthalpy. So our third problem is about solving the final temperature of a universe. We have this problem. 83 grams of iron was placed inside a bowl with 850 grams of water. The iron and the water has initial temperature of 764 degrees Celsius and 16 degrees Celsius respectively. So what is their final temperature? In this problem, I drew a concept of a universe wherein the water serves as your surroundings here, right here, and the iron serves as your system. So I derived with this equation. The heat of water is equal to the negative heat of the iron. So why is it is negative here? So as you can see, 764 degrees Celsius is warmer than 16 degrees Celsius. So the tendency of iron, it will release heat and it will be absorbed by the water. So knowing the specific heat capacity of water and iron, we will be able to find their final temperature. If you can remember, the formula for heat is Q is equal to mCat. So we will be just plugging in the information here. So 850 grams of water, specific heat of water 4.184, and final temperature, which is the one we are solving, and initial temperature of 16 degrees Celsius. And the negative, don't forget the negative here, 83 grams, 0.44 capacity heat, and the one we're looking for minus the 764 degrees Celsius. That's hot. So we will be multiplying these two, and we will be distributing it to the final temperature. So we will be getting, if you calculate that in a calculator, 3,556.4 EF, and after that you will distribute it to 16 degrees Celsius. And the result is 56,902.4, which is equal to, we will be multiplying these two again, and then we will distribute it to TF and to 764 here. So it will be 36.85 TF and minus 28, 4.93. And remember that we will distribute this negative sign because it released heat. 2.85. This will become positive 0.93, and we will be just copying these numbers, just the same. And then finally, we will transpose this TF to here, so it will become positive 36.85 TF, and this will go there, 56,902.4 plus 2,154.9. So we will be adding these two, so it will turn 35.25 equal to 85,057.30. And then you will divide both sides with 3,593.25. So TF is equal to 23.67 Celsius. So this is your final temperature for this universe. Our fourth problem, I'm going to teach you how to complete a nuclear reaction. We will be solving alpha decay, beta decay, and gamma decay first. But first, you will be needing this periodic table. This will serve as your guide in finding the elements needed to complete the equation. So first, in alpha decay, this is your main target, the helium element. So you need to find an element that when it will be added to 4, it will be 230. It will result in this. So you have to minus 230 by 4. So you will write 226. And like this one, we need to subtract 2 here. So it will be 88. This is the atomic weight of the element, and this is the atomic number of the element. So you will have to find the 88th element on the periodic table, which will result into our A soon. Radium. Radium. This is radium. Okay. The next one is beta decay. So the highlight on this decay is this. This is an electron, and this is an antineutrino. So you will think of an element when 92 is subtracted to 1, it will give you the 91 element. So you will just copy the atomic weight because there's no added in here, value here, so 234. This may vary from, because periodic table is not consistent with its atomic weight, so it's not really important, but this is really important, the number of protons or the atomic number of the element. So you will find the 91 is protactinium. So Pa. So the next one is gamma decay. This is like beta decay, but it has an additional symbol, which is stands for gamma, which is the symbol of this. So just like in beta decay, you will have to find an element, which is when it is subtracted by 1, you will get this number. So of course it's 15, and you will have to copy, since it's 0 here, 28. So you will find, what's the 15th number on the periodic table? It's phosphorus. So that's it for the first 3. So the final 2 reactions is positron emission and electron capture. So we will be solving this equation. So positron emission is just the positive sign, or the positive one here is present. It is not negative, obviously, and this is not an anti-neutrino anymore. It's just a neutrino. That's why it differs from beta decay. So it is called positron emission. So you will think of a number that when it is added by 1, it will give you 6. So obviously it's 5, so you will just have to copy the atomic weight. So you will just have to find the 5th element, which is boron. Yeah, voila! You've completed the equation for positron emission. Number 5, the last nuclear reaction we have here, or equation here, is electron capture. Or sometimes it's called K capture because of, I think, of the shells, K shells, about that. By the way, or anyway, so in this equation, you will have to capture an electron, based from my understanding. So it captures electron here, but in here you have only a neutrino. So remember that it is not an anti-neutrino. So you will think of a number that when it is subtracted by 1, it will give you a 37 number. So obviously it's 38. And you will have to copy the atomic weight. So find the 38th element on the periodic table, which gives us 2 strontium. And that's it, guys, for our nuclear reaction equations. Our last problem is about carbon dating. So we have this problem. A tiny sample of cloth was discovered in the middle of the desert of Egypt. It is burned to carbon dioxide, and the ratio of carbon 14 to carbon 12 is 0.350 times the ratio in today's atmosphere. So how old is the cloth? So we have to know what is the half-life of carbon. it's carbon dating. So we have this years, which is 5,730 years. And first, we have to find the value of K, which is rate. This is a rate constant or decay constant. So finding K is ln2 over the half-life. So ln2 is approximately 0.693 over the half-life, which is 5,000. And you will get 1.21 times 10 raised to negative 4 per year. So this is the decay constant. And the next thing you need to know is this formula. And it will give you a derivation of this formula to know how old it is. This T stands for time. So T is equal to 1 over your K, which is this 1.21 times 10 raised to negative 4 ln. The original, which is 100%, it will be just this one. And N stands for the percentage of this, which is equivalent to 0.350. So just plug in these numbers in your calculator, and you will get 8,678.50. And since it is in years, so we have to round up the numbers. So 8,679 years old. So this is the answer for this problem. And that's it for today, guys. Hope you learned something. Thanks for watching.